Well, I'm sorry, I misspoke. I said I was gonna talk for 10 minutes. Can you talk for 10 minutes?
No.
No, it's not true.
It equals a vector.
Yeah, I think if I add any two vectors in 2 space, I'm gonna get another vector. If I add any two vectors in 3 space, I get another vector. I got a phrase for that.
Yeah.
If I add too many mathematical entities together and get the same kind of mathematical entity, I say that that operation, in this case addition, is closed. So I might say that vectors in 2 space are closed under addition, or maybe even vectors in 3 space that you guys are used to are closed in under addition. What about this one? If I take a vector in 2 space or 3 space, I don't care which, and multiply by a constant, what do I get? Another vector. I'll rephrase this in English. I'll say that vectors have closure with scalar multiplication. Do you think this is true? I'm sorry, maybe not that. How about this?
Yes.
I do think addition contributes. Do you think this is true?
Yes.
So I might say in English, vector addition is associative. What about this? Do you think there exists, have I used a symbol in class?
Mm-hmm.
Do you think there's a special vector called a zero bar such that no matter what u bar is, if I add zero bar to it, I'm going to get u bar right back? Yeah, I think there's a zero vector in the appropriate space. And I think this is true for all vectors u bar in my space, whatever it is, R2, R3, doesn't matter which. Do you think for all vectors u bar that there exists something like this? Such that I can add to u bar this new thing and get the zero vector right back.
Yes.
So I also do, I'm just rattling off on this inkboard certain qualities that vectors have relative to the operations of addition and scalar multiplication. You guys, what am I missing? How about this? If I take u bar and multiply by 1, what do you think I'll get? What if I take u bar plus v bar and multiply it by scalar? What do you think I'm going to get?
Yep. K U V bar.
What's going to happen if I take two scalars and multiply by u bar? What do you think I'm going to get?
C U bar. K U bar.
You guys, isn't this natural?
Yeah.
What if I take a constant c times a constant k times u bar? Do you think I'm going to get the product of those constants times u bar?
Yes.
I just think these are a lot of basic qualities you and I take for granted that vectors really behave by in both 2- and 3-dimensional space. Yes, Michael?
What does the upside down mean?
I sometimes refer to this as my universal quantifier. It stands for the phrase for all, or for every. What if f and g are continuous functions? And they're defined over the entire reals. Do you guys think that if I add f and g together, I'm going to get a whole new function h that's continuous over the entire reals? Yeah, I do too. And maybe I can take some time and show you that such functions satisfy all these conditions. They behave just like vectors. Do you think if I take two matrices and add them together, do you think addition commutes? Oops, I said, do you think addition commutes?
Yes.
So maybe matrices as well not only satisfy that one commutative property that all the vectors of R2 and R3 have, maybe they satisfy all of them. Actually, excuse me, I'm going to change my language. I'm going to talk about these axioms and proclaim that if any system of things abide by these axioms, I'm going to give the whole set of those things a whole new name. I'm going to call them a vector space. And I maintain I got a whole collection of axioms. I'm now going to show you that collection of axioms. You guys don't look yet. I'm going to get you blurry. I'm going to give you headaches. I'm being blurry. So long.
Oh, now I've got a headache.
I apologize in advance.
tell you not to look?
Yeah, but I didn't listen.
Just made you look more.
Yeah. It's like when people tell me not to look into the sun.
Do not. You guys don't commit these to memory, okay? In a test situation, if you need these, I'll give it to you in paper form. I just expect you to be able to use them. So, let me start off my discussion. Let the set V be a non-empty set, meaning there's something in it, whose elements are going to be called vectors, where there's an addition and scalar multiplication defined, with a collection of scalars that are a set called F. Now, I like the name V for the set, because I'm eventually going to talk about a vector space. I like the letter F because, technically speaking, the set of scalars have to satisfy their own properties. And you will not find in this textbook what those properties are. It's beyond the scope of the course.
Try it again.
Oh, it won't work. It's broken. I can keep trying if you like. But the reason why the authors use the letter F is because the properties, the own axioms that set of scalars satisfy is called a field. So that's why we choose the letter F. And if you want to Google field, it'll give you all the characteristics that a field has. For me right now, I'm just worried about these axioms for which a set's going to have to satisfy if I'm going to call it a vector space. So if I got a set V with its corresponding set of scalars that satisfy all 10 of these conditions, I will call it a vector space. And the axioms you see on here might be in a different order than I rattled off, but they're just simply the characteristics. You seem to agree with me in a short 10 minutes that vectors in both R2 and R3 really do satisfy. So, can I spend today in just making up some examples of sets, and you and I can determine whether or not they're vector spaces? Now keep in mind, when it comes to these operations of addition and scale multiplication, I can define those any way I like, as long as I satisfy these axioms. So, you guys, I want you to consider the very special set, namely the set containing the singleton element 1. And S is going to be this collection of all real numbers. That's my set of scalars. And I'm going to define addition in such a way that 1 plus 1 equals 1. And k times 1, no matter what k is in the real number system, is equal to 1. So, does that form a vector space? Yeah, I think it does. I think for free, my very first axiom is being satisfied. Closure for additional holes. After all, look at the way I define addition. There's only one element I can add to, and it's going to be 1. I think for free, axiom 2 is satisfied. I've got closure for scalar multiplication because any real number times my one element to my set V is going to be that one element V. I think associativity, I misspoke, sorry, I'll come back up here. I think commutativity holds for free, after all. With that third axiom, let's take this arbitrary element V. Oh, there's only one of them. Add it to this, well, this arbitrary element V, it's still only one of them. And let's see what happens when I reverse the order. Don't I get this in both cases?
No.
See, I think I do, because I think 1 plus 1 by definition is just 1. But this 1 plus 1, well, it's in positive form. And I think associativity holds after all. If I add 1 plus 1 and add 1 to the result, let's check out what we get. Inside the parentheses, what is that?
1.
But what's 1 plus 1?
What is okay, we defined 1 plus 1 equals 1, but does that really mean anything?
Well, it means a lot to me. It means the set's got this very nice quality that when I add something to itself, I get the thing right now.
Well, oh, okay. When you say this is it, you're not adding them together, you're doing something.
Oh, I'm
so
adding them.
You have defined an addition over this vector space.
Careful, I've defined addition over the set. I haven't proven it's a vector space yet. I gotta go through all the
So
axes.
you define an addition over this
Set.
set. So, okay, can we use a different symbol other than plus? Just like a hash or a...
You know, what a good question. Yeah, I would love to, but the author doesn't. So I was just trying to be consistent.
Okay. But we can't say, I'm sorry, I'm taking so much time. But we
No,
can't
don't
say
apologize.
that addition is different from addition of Windows.
Sure.
This is where you're breaking down all he knows about math.
I know. It's gonna look very different. We're gonna look at some funky different operations. So both scalar multiplication and addition at set B. I'm not
You
done.
said this was supposed to be boring? This is hilarious.
No, I said the first 10 minutes when I talked about R2 and R3.
Oh.
Now I'm getting more extreme. You know what? I failed to verify the axiom of associativity holds. I only looked at the left-hand side. So let me come in and let me take the right-hand side. You guys, you do the arithmetic for me. What's 1 plus 1?
2.
What's 1 plus 1?
1.
Ooh, I just showed you that the the fourth axiom is satisfied. What comes next? Is that the existence of a zero element? Clearly, my zero element is.
I don't know.
Yes, you do.
Is it 1?
Yes, thank you.
Ah!
Because I think that zero element, there it is, added to anything in my set, well, there's only one thing, is going to be
1.
1. So I think that particular axiom is being satisfied. Does there exist a negative V bar? Of course
You'd
it
have
is.
to.
A negative V bar is going to be equal to 1 because I think when I add that to my V bar, I get the 0 bar.
1.
What about the next axiom? Do you think if I take the real number 1, do you think if I take the real number 1 and multiply any vector in my vector space, I'm going to get 1?
Yes.
Oh, thank goodness. That would be my V bar. Do you think, well, I shouldn't say do you think. Tell me what happens when you take an R times an S and you multiply to V.
Was a 1.
You just get something 1. But what happens when you take R times S times 1? We'll show you steps. R times 1. But R times 1 is.
1.
Yeah, what about axiom 9? I'm being honest with you guys, I don't remember the actual order of these axioms. I'm running out of room. Can I raise up top? If I have an R times U bar plus V bar, do what's inside the parentheses. What do you get?
R times 1.
But what's R times 1?
1.
Stop. Let's take a break. Let's take a peek at the sum of R times a U bar plus an R times a V bar. Whoops, I put V bar in there. So help me, turn by turn. Turn
1
by
plus
turn. What
1.
do I get here?
1 plus 1. Plus 1.
Which equals?
1.
Oh, thank
1.
goodness. And lastly, if I take an R plus S times a V bar, don't I just get
1 plus
1? It's just that when it comes to R times 1 plus S times 1, I think the first product is plus. Oh, you guys are on a roll. Just one more time. No pun intended. That was not intended. What, did you get 1?
Yes.
Okay, so we just proved that that particular set over the set of scalars with this defined operation of addition and this defined operation scalar multiplication does indeed satisfy my 10 axioms. I can now refer to the set as a vector space.
I don't understand how it satisfies 6.
Part 6?
Yes.
Well, let's do this. Key into these words. I'm trying to see if there exists such a thing as negative V bar. Such as this is true. So, symbol by symbol. I think V bar has to be, well, actually this. We've already shown 0 bar is that. So let's put a question mark here. What would I put in for question mark so that this is a true statement?
1.
Okay. That's,
We just proved that question mark is 1, negative bar is 1.
okay. I thought it was, the way I was thinking about it was like you're subtracting one from itself to prove that you can get 0, but because 1 equals 1 plus 1, you'd end up with 1, and that wouldn't satisfy it.
I see your point.
Yeah.
Chris?
Can we call it the loneliest vector space?
No, I think, yes, you can. Yeah, you can call it the loneliest vector space. And if I replace,
So you could just replace 1 with any, 1 doesn't really even matter here. It could be any value, right? If you put like 3 plus 3 equals 3, you could do the same thing.
Oh, Earth? It's an O.
Earth plus Earth equals Earth.
yeah, I agree with you.
What is it?
Chris?
Yes.
I'm listening.
What is Earth? What did we define it as?
I didn't. It could be anything in normal, please. That's my whole point. You don't like my ones, call them whatever you want. As long as you define the addition operation like that, scale multiplication, it still holds true. Who cares what you call that sigma 1? What about something like this? Same question. Do we have a vector space? This time for this example, if you guys don't mind, I'm not going to show all the axioms. We're just going to dive in and we'll just talk about a few of them. I don't want to spend all the class with just one example. Although the first example was pretty good. So, look at my notation. When I use a notation m subscript 2, open parentheses r, close parentheses, I'm really referring to the set of all 2 by 2 matrices where the entries are real numbers. So, you guys just give it a minute and think about whether or not this really does form a vector space. Any ideas? I see one head nodding, 2 heads nodding.
I don't think there's necessarily multiplicative inverse for all 2 vector matrices.
Whoa, what a good point. And notice that with my set of axioms, I never even addressed the issue of multiplication of vectors. No, nowhere do we see that. Now, I do want to talk about an operation multiplication with vectors if I got a vector space. I'll give it a special name. I'll call it an inner product, which, by the way, is going to be an exact duplicate of the dot product you saw back in trigonometry. But I need to sit down for a while and just talk about vector spaces first before I dive into an operation. I was hoping you guys wouldn't take too long. I was hoping you sort of say, I gotta relax. Since matrix addition is defined in terms of the component-wise addition, and they represent real numbers, that these axes are probably all gonna hold, and they do. Can I look at a few? Let me show you how to show associativity holds. Now, you gotta keep in mind, this is an exercise of showing what you might think is a bloody obvious, but you gotta show it. And so if I were to show associativity holds, like for example, axiom, is that number 4? I would say, let's consider elements A plus B plus C in my set V, and I'll do the addition here first. And since I'm just in M2, I don't have to be that abstract. I'll choose 2 by 2 matrices. I've got an A1, A2, A3, and A4, plus a B1, B2, B3, and B4, plus a C1, C2, C3, and C4. And clearly, that's equal to this. Do you guys agree?
I feel like you skipped steps.
How many?
3, Peter?
Quite a few. I think I'm horribly off base, you guys. Think about it. I got to go back into the components. As a matter of fact, I started off to say, let's add A and B together first. So I think my parentheses are off. Secondly, I think I need to show you, the reader, what the heck happens when I add these 2 matrices. I think I get this. Did you guys see my point?
Yep.
Plus this matrix. parentheses are necessary at this point. I'm just adding two matrices. Oh, I'm adding two matrices, I just said that out loud. I guess I can come in and say this. I've got, the sum of these two matrices is gonna be A1 plus B1 plus C1, A2 plus B2 plus C2. If I'm gonna show all my bloody details, are you guys happy so far? Are you happy so far? I can ask that a third time.
No.
No, I'm not happy either. If I'm gonna add these two matrices together, I think what I really show you, the reader, I'm doing, is I'm taking the entry in the first row, first column of the first matrix, and adding it to the entry in the first column, first row of the second matrix. Do you see my point? However, it is the case that the entries in this matrix represent real numbers. And we know the operation of addition with the real number system associates. And so I do think I can reassociate the addition with the first entry, the second, and the third. Did you guys see my point?
Yep.
Again, keep in mind, this is an exercise in showing the bloody obvious. I'm running out of room, I apologize. And I think this is nothing more than the sum of these two matrices. Be careful with my choice of words, I did make a mistake. As I said, these two matrices. Okay, maybe not these two. These two. But I think this is nothing more than the following. And I think that's nothing more than this. You guys, I'm sorry, I know there's a lot of tedious writing. I'm just trying to press upon you what you need to show me that this particular axiom does or is not satisfied. That's what I'm looking for.
If the problem had instead asked for, well, if it had defined B as the set of all matrices, n by n matrices, it would probably be more right?
I would use the open bracket, C sub I j, close bracket. I would.
Wait, open bracket then close bracket?
Open bracket, A sub I j, close bracket.
Oh,
That notation, the component-wise notation. I agree. Do you think, you know what, I gotta stop for a minute, you guys. I've never done this in class. I've never opened the book and brought this up. It's just that with my memory stick, I left it in my office this morning. And so I have my own sheet that would be easier to read. And since I'm the one who typed it, I wouldn't probably write these vectors with a boldface. I write them this way, with a bar over it. And you need to understand, because it's so unclear when you're looking at the board in class today, you need to understand that that zero is bold-faced. That is a zero element of the original set. Do you think there exists a zero element in this particular example?
yeah.
What is zero bar?
Zeros.
It's a 2x2 matrix with zeros in every single position. That would be zero bar. Do you think axiom 1 is being satisfied? Do you think I have closure for addition?
Yeah.
Yeah, I think adding two matrices with real entries gives you another matrix with real entries. Do you think scalar multiplication holds? It does. Can I stop? I do insist that each and every one of the axioms is being satisfied. So I do think this set forms a vector space over the scalars.
Great question.
Yes, sir.
Do you not need the curly brace notation when you're saying B equals M such group 2?
Correct. I don't need the brace notation only because M sub 2 itself is a set of 2x2 matrices with real entries.
Vector multiplication never has to be satisfied.
Say one more time, I'm sorry.
Vector multiplication doesn't have to be satisfied.
Scalar multiplication does, yes.
Yeah, but not vector.
True. If you look at this definition of a vector space, it doesn't even address the issue of multiplication. And not every vector space does have a clean multiplication operation defined, but some do. And when they do, you're going to see this in a couple, well, several days. When they do, I might subclassify the vector space as an inner product space. when it's got a special multiplication process. Do you think that forms a vector space? Oh, sorry, hold it. I never told you what that was. What do you think?
Well, that's just the elementary matrix, isn't it? Or one of those.
So you're saying I can take a break and just sit for a minute.
Because A can be any number, right?
Yeah.
So
Does this set V form a vector space over that set F?
Doesn't have the zero.
Danny, why not?
Because if you try doing the, like, for closure under addition, if you try adding it to itself, you'll get A being some real number, 0, 0, but then you get 2, and that doesn't make it an element.
Yet somebody else over here said there's no zero element. I like that. But also it's the case that there's no closure for, which one of the
The
operations?
first one.
Which one?
Closure, addition.
Or
scalar multiplication.
Or scale multiplication. I don't think I have closure. Watch. Here's what closure is all about. Put on my tabletop all the elements of V. If I just take any two elements, add them together, do I get another set that's on my table? I'm sorry, I misspoke. I said it too poorly. Consider all the elements of V that are on my, that are situated on my tabletop. All the elements of V are here. Is it the case that no matter what two I grab, if I add them together, is something else on my tabletop? If the answer is yes, I got closure. But if I can find two elements on the tabletop that I add together that are not on my tabletop, I don't have closure. And certainly, if I were to add this one to this one, question, are each of these two matrices in set V? If I add them together, do I get another element in set V?
no.
No, I don't, because this third entry, this fourth entry, excuse me, will be a 2, not a 1. So I don't even think I have closure for either one of those operations. Therefore, I do not have a vector space.
Well, why do you care so much about addition but not necessarily multiplication?
Now, that's a really good question. Because there are too many mathematical sets out there that behave just like the traditional set of vectors you know in R2 and R3 relative to the operations of addition, scale, multiplication, but don't have a corresponding definition of multiplication like you saw back in R2 and R3. And if we reject the multiplication that you had in R2 and R3, whether it's a dot product or cross product, what remains is something that's so significant, you and I can develop some theory on it, and then apply to other sets that satisfy the same axioms, that don't necessarily have the multiplication operation. The weaker idea of having no multiplication still gives us something as an object that has really rich flavor and characteristics, mathematically speaking.
I'm just thinking, does it not care that much about multiplication because the normal like scalar multiplication that we know can really just be broken down into multiple additions, but then there's a different types of multiplication, like when we do vector cross product, you could call that like a multiplication.
The only reason why that makes me nervous is because when it comes to the scale of multiplication, it might not be defined in the traditional fashion, but it still might have a vector space. So I'm just kind of a little hesitant to say that the scale of multiplication is necessarily interpreted that way, as repeated addition. Michael?
So is the V that's shown over there different from the V bar? Like, is it?
Oh yeah, sorry. That number one should be an uppercase V.
Okay.
There's no bar over. If it had a bar over it as a single vector, no bar over it, I'm simply talking about a whole set of things. What do you think? Sorry, you guys, I'm not trying to stall today. This is just a thinking day. This is new for you. I want you to take a moment and just look at what that is, decipher what they would look like in terms of elements of a set, and just imagine whether or not you think they satisfy these axioms. So Dan's already saying yes.
Yeah, I think so.
Yeah, I do too. I think I've got all quadratic expressions where the x term's missing, because a sub naught and a sub 2 range over the reals. I think if you add any of those two beasts together, you get another one of those beasts. I think if you multiply those beasts by a scalar, you get one of those tiny beasts. I think it has a zero element. It's just zero itself. I think any a sub naught plus a sub 2x squared has an additive inverse, namely negative a sub naught minus a sub 2x squared. Clearly the scalar axioms seem to be satisfied because they're just multiplying the other scalars, a sub naught and a sub 2, in the real number system. Can I wave my hands that fast? That seems like this axiom is being satisfied without showing the details. Chris?
Whenever we specify a field, that only matters for our scalars, right?
Can you say it louder? I'm sorry.
Whenever we specify a field, does that only matter for our scalars? When we're talking about that?
Yes, it only matters for scalars. Yes, I agree. And those scalars could be something completely different. They could be different entities than what you see in the set V, like my first example, where I had single to set 1, but the scalars range over entire reals. What do you think of this vector space? I misspoke, sorry. I meant, what do you think about this set? You think if I add any two nth-dimensional, do you think if I add any two nth degree polynomials, I'll get another nth degree polynomial or less? Yeah, I do. And who cares if the a's and n's cancel out? It'll still be on that form because that last coefficient, or maybe a lot of them are going to be 0, that's fine. Do you think if I multiply any nth degree polynomial by a scalar, I'll get a polynomial of degree less than or equal to n? Yeah, I do too. In fact, I think each of these axes are going to be satisfied just like they were with M2. Because I'm just dealing with the traditional operations of addition, scale, and multiplication in the real number system. It's just that this one has to be so important. Can I give it a name? I shouldn't say this. Your author sometimes refers to this. I really don't like this. I'm very much against this notation. He calls it piece of man. So I will struggle in class by trying to remember. He calls it piece of man. Chris? I despise it for this reason. When you take a peek at this arbitrary element, I think it's a linear combination of these individual items. Sorry, I misspoke. These individual items. I might even refer to this like I will this week. Well, tomorrow or Monday, I forget which. I might even refer to the set as a spanning set for the vector space because I think every element in this vector space is generated by looking at a linear combination of these pieces. How many elements do you see in here?
N.
I can hear you.
X plus 1. N plus 1.
N plus one of them. And I would like to see the subscript correspond to the dimension of that thing I'll call a basis in the near future. And it often doesn't do that. I think he actually did do that. He did do it my way at earlier editions of this textbook. As I recall, it's been a while. But he certainly doesn't with this current edition.
Well, it's only because it starts discounting at 0.
Oh, I know, but you know what? I don't care where you are in this country, East Coast to West Coast, no matter what university or college you're at, here is going to be the very last sentence in any linear algebra course. Here is the end be all. I'm going to give it away today, the first serious day. The last sentence any professor will say in a linear algebra course is, okay, any vector space of dimension n will be basically the same as Rn. I don't use the phrase basically the same as. I'll use the word isomorphic. But any vector space of dimension n will be isomorphic to Rn. And so let's keep n as the dimension of that vector space. Or how many elements are in a basis for the vector space. So that's why I really get knocked off in class when I talk about piece of n. I'm just not used to thinking this. disagree.
Maybe it more specific.
I do agree.
X3. Oh, you have the same scalar for every, yeah.
Yeah.
So I think I've got a set of all n-degree polynomials where each and every coefficient is the same.
Well, then it's not closed.
Well, that's exactly what that is, what you wrote down there, right?
Well, true, but be careful. That was my set V though. I was saying this is a generating set for this V.
Wouldn't that set V then be, wouldn't you need an n in front of every x? Because if you're saying that each scalar is different in that set.
Yeah, don't look like because I was going way ahead of the game. I was talking about something called the basis. And if you're to let this be set V, it's definitely not a vector space because if I add x to x squared, I get x squared plus x, which is not in this set. Anybody have an intuitive feel whether or not this is a vector space?
It's not if you define addition.
Thank you. You know what, Chris? I should have said that. I meant to say addition and scalar multiplication are defined in a traditional fashion for polynomials. I meant to say that. That's my mistake.
Well, the generator here was that it's not closed under addition.
Let's check it. So check enclosure for addition. Did I use my black pen already? Oh, excuse me, I'm going to keep that up there. Let P be equal to sum as I play this game. And let's let Q be equal to this. If I'm going to check vector addition to see if I got closure, consider R to be equal to P plus Q. And determine. If indeed my R is an element of my set V, and if the answer is yes, I've got closure because I chose arbitrary elements P and Q in the original set V. So let's give it a shot. I think when it comes to R, this is equal to P plus Q, but this is nothing more than the sum as I play this game. Excuse me. My apologies. Plus this. Oh, but you guys, we know something about sums. As long as I is ranging from the same initial position, same terminal position, don't I just simply get this?
Yep.
But doesn't that just simply give me this? You guys, did I just make a mistake? I really did. I meant R to start at 0.
Yeah.
My apologies. As I range from 0 to n, if I factor out the x of I, don't I just get this?
Yep.
But isn't that the same as this? This is, you know, I don't know what it is. Can I give it a